Assalamualaikum and hello. My name is Muhammad Manfidaus and my role is as student 1 for our group project Smart Indoor Comfort Monitoring System using Arduino. My task focus on integrating and configuring temperature and humidity sensor with Arduino to process data and setting temperature threshold. For temperature, I use the LM3510 temperature sensor connected to Arduino analog pin A0. For humidity input, I use soil moisture sensor connected to pin A1 which calibrated to give humidity percentage value. In Arduino code, I wrote custom function to read the analog values from LM35 and humidity sensor, and then I convert the LM35 voltage into Celsius temperature and map the soil moisture sensor reading into a percentage scale to present humidity. This function ensures that data is ready for both display and control decision making. I also set up the temperature threshold in the program. Cold is below 20 degrees Celsius and comfortable between 20 and 26 degrees Celsius. Hot is above 26 degrees Celsius. This criteria allows the system to automatically adjust output. For example, turning the fan when it's hot, turning the fan on when it's hot. I also test the sensor integrated simulation by adjusting input values to check either if the reading are displayed correctly on the LCD and serial monitor, and if the system read as expected when thresholds are crossed. As conclusion, as student 1, my role is to ensure that our temperature and humidity system is accurate, responsive, and able to categorize comfort level, which conform the foundation for the system control logic. That's all. Thank you.
Hi, I am Mukis, and for our Smart Indoor Comfort Monitoring System, my role is to integrate and calibrate the light intensity sensor. This sensor helps the system decide whether to turn on the lamp LED automatically. We use LDR or light dependent resistor connected to analog pin A2. When light hits the LDR, its resistance changes, producing a voltage that the Arduino reads. In bright conditions, the resistance is low, and in darkness, the resistance is high. In the code, we read the light level using analog read light pin. The value ranges from 0 to 1023, and we compare it to a threshold of 500. If it's above 500, the system says bright, and if it's lower, it says dark. This threshold can be adjusted depending on how sensitive we want the system to be. In auto mode, if it's dark, the lamp LED turns on, and if it's bright, the lamp stays off to save energy. In manual override mode, the lamp is controlled by a slide switch, ignoring the sensor. With this setup, our system responds intelligently to the environment, keeping the room well lit only when necessary, and reducing energy waste.
Hi, my name is Muhammad Danish Shahmi, and my role in this project was to control the comfort response system using actuator. In our Smart Indoor Comfort Monitoring System, my responsibility was to make sure the LED indicators and fan respond correctly to the temperature and humidity readings from the sensor. The goal was to visually show the comfort level using LEDs and to turn the fan on automatically if the temperature went above the threshold. In auto mode, the LEDs indicate the comfort zone. Yellow LED means it's cool, green LED means comfortable, red LED means it's hot. When the system detects a hot condition above 26 degrees Celsius, the fan is switched on automatically. If the temperature is below 20 degrees Celsius, the fan stays off and the yellow LED is active. Between 20 degrees Celsius and 26 degrees Celsius, the green LED is on and the fan stays off. In manual mode, the fan is forced on and the red LED stays at 50% brightness to show it's under manual control. Here's a quick demonstration. You can see how the LED change depending on the temperature and how the fan turned on only when needed in auto mode. It's ensured the system keeps indoor condition comfortable while also saving energy. That's my part of my project. Thank you.
Hello, my name is Abdul Rahman and my role in this project is to implement the manual override and the safety feature for our project. Let me start with the manual override first. So during the normal operation, the light is controlled automatically based on the brightness of the environment or surrounding area. So for example, if the surrounding area is too dark, the LED light will be turned on. But if the surrounding area is too bright, the LED light will be turned off. So the problem is now that the user sometimes want to control it manually. So that's why I added a push button to enable the manual override mode. So as you see that if the surrounding area is bright or dark, the LED light won't be affected by it. That's why I added the switch button. So if the user want to keep the light on, then you can turn on the switch. But if the user want to keep the light off, then you can turn off the switch. Now for the safety feature, as you see we have the temperature sensor here. So if the temperature sensor failing, for example the temperature is above the threshold temperature, which in this case we set it to 100 degrees, the system will respond by displaying the system error and immediately on the safety mode. So when this happens, the red light will keep blinking to alert users that the temperature sensor are failed.
My name is Zuhair Farhan and my role in this project was monitoring and output display for our smart indoor comfort monitoring system. As you can see in the simulation right now, my part is responsible for showing all the important readings on the LCD in real time. On the first line of the LCD, we have the temperature in degrees Celsius and the humidity percentage from our soil moisture sensor. On the second line, we have the light condition, which will change between bright and dark, and the override status, which shows yes when the system is in manual mode and no when it is running automatically. So if you watch closely, when I change the temperature in the simulation, you'll see that the number on the LCD update instantly. At the same time, the LED indicators and the fan respond. For example, when the temperature goes above our threshold, the LCD shows that the higher value and the red LED turns on and the fan starts spinning. Similarly, when I adjust the soil moisture sensor, the humidity percentage on the LCD changes. This helps the user know exactly how dry or how moist the environment is. For the light sensor, when I reduce the light level in the simulation, you can see bright on the LCD change to dark. At the same time, the white LED lamp turns on automatically. If I switch to manual override by pressing the push button, the LCD instantly updates the override status to yes, and in this mode, the lamp can be controlled directly with the slide switch. In the coding, this display is managed using the liquid crystal _L2C library, which allows us to send text to the LCD over 2 pins using the I2C protocol. The system updates this value every second, so the display is always accurate. We also send the same readings to the serial monitor for testing and debugging purposes. Overall, my part ensures that the user can clearly see all the environmental readings and the system mode at a glance, making the system both user-friendly and easy to understand.